Hello everyone, this is the last video for the lab portion of biostats. We will cover chapter 19, which is regression and correlation. To start, I have a couple of notes on this chapter, and of course I'll post these slides. For lab portion only, we're skipping the following sections. So I've listed those section titles here. Those are on pages 248 through 250. There are portions of those pages that we are going over, so don't just skip over those pages entirely. We are also skipping over all the step-by-step math because we are using Excel and R. So here's a chapter overview. We'll be covering the difference between regression and correlation, how to do both, and the significance and interpretations of these two tests. So first of all, what is regression? Regression studies the relationship between a numerical treatment variable and a numerical response variable. There's different words to describe these two variables, and I've listed them all out here, but the basics of it are one variable can be manipulated by the researcher, and the other variable is not manipulated, it's just observed. With regression, we can predict values of y given values of x. So x is these treatment or controlled variables or manipulated variables, and y is those observed variables. In regression, the slope of the line does matter, and it can imply causation. Then we have correlation. This studies the relationship between two numerical non-experimental variables. So these are just observed variables. Neither one is being manipulated in that study. It measures the strength of association between x and y. The slope does not matter, and correlation never implies causation for the purpose of our statistics course. Here are some examples of what those can look like in graphical form. The other thing that's important to note here is that both regression and correlation assume a linear relationship between the two variables. They also use the same fundamental math, which again, we're not going to be doing the step-by-step math, but these mathematical calculations, these tests that we're doing, lead to different types of conclusions. So on the left here, we have an example of regression. So we have dollars spent on advertising on the x-axis and monthly sales on the y-axis. This dollars spent on advertising is something that can be manipulated and controlled, so that would be a treatment or independent variable. The monthly sales is an observation or a dependent variable, so this would count as a regression analysis. Here the slope would matter and we can make predictions. On the right side we have correlation. We have the number or the average number of leaves per branch and the number of infectious nodes per plant. So neither of these can be controlled or manipulated by the researcher. They're both just observational variables. So here the slope does not matter and we cannot make predictions from an equation. So I'm going to start with correlation because it's a little bit easier than regression. It's just a very short analysis. So we're going to start there and then go ahead and do regression. So as I mentioned, the purpose of correlation is to measure the strength of association between two numerical, non-experimental variables. This can be observational data or data where you don't know which variable is the independent or controlled variable. The mathematics of correlation relies on something called the sum of the cross products to take both variables x and y into account. The ultimate calculated statistic for correlation analysis is the correlation coefficient, and this is represented by the Greek symbol rho for population analysis or a lowercase r for sample analysis. The way we're going to calculate it for the lab portion of this class, we're going to use the data analysis toolpack in Excel in order to calculate tcalc and our p-value. And in R, we'll use a very short function called core.test with the y variable of the data and the x variable of the data. So as I mentioned, the correlation analysis leads to the statistic of a lowercase r, and the range for this value is -1 to +1. A higher absolute value of R indicates a stronger association between these variables. So a very positive near 1 value indicates a strong positive relationship. A very negative, such as negative 0.09 or 0.9, would indicate a very strong negative association between those two variables. If R is equal to 0, this implies that there's no association between the two variables. So I'll show some examples here of what these might look like on a graph. The first one has a very tight correlation and it's very positive. This could be an example where R equals 0.9. Here we have still a positive association, but the points are a little bit more spread out. It's not quite as sharp and striking as the first one, so this might have an R value of 0.5. Next, we have a pretty dispersed group of points, but they do seem to be following a downward trend. So this may represent an R value of negative 0.2. And finally, we have now a more sharp and distinct downward slope to these points. It's still pretty dispersed, not quite as tight as that 0.9 from the first graph, so this might have a correlation value of negative 0.4. With that said, we always do need to test for significance with these values. So you can calculate these statistics, but it not be significant. So we do need to use the p-value to test if this is a significant correlation or not. To do that, we have our null and alternative hypotheses. The null hypothesis for the correlation analysis is R equals 0. There's no association between the two variables. Our alternative hypothesis is that R does not equal 0. They are somehow related. This is a two-tailed test because we are not interested in which direction. We just say there is some difference. Ultimately, a t-test is used to test for this significance. R does it for you, and it's very easy to do in Excel, and we'll see that. We'll calculate t-calc with the equation shown here. It's equal to the correlation value multiplied by the square root of the number of observations minus 2 divided by 1 minus R squared. And that R squared is different from the capital R squared, which we'll see with regression. Then we calculate the p-value with the t.dis.2t formula, which we'll see in Excel as well. Then to interpret this, as always, if p is less than alpha, we reject our null hypothesis. This would mean we would conclude that the correlation is significantly different than 0, and there is a significant association between the variables. That may be positive or negative, depending on the sign of R. So what we'll do now is take a look at a practice problem in Excel. We're going to plot the data to see if it is linear. That's the number one assumption we need to look for correlation analysis. We'll use the data analysis toolpack, calculate t-calc and the p-value, and interpret that data. So let's go ahead and open up the lab manual to page 251. And this is the data we're going to work with for the examples of correlation and regression. In the lab manual, this does go through all of the math, but we are not going to do the stepwise math because we have tools that will do it for us. So in this example, we don't have to consider whether this is a regression or correlation question because we're just going to do both for the purpose of demonstrating the steps. At the end of this video, we'll take a look at a couple other questions to understand how to determine if it should be a regression analysis or a correlation analysis. So moving into Excel, I have the template for this chapter up, and the original data is here, X and Y. The first thing we need to do for either a regression or a correlation analysis is make sure that this data meets the assumption of linearity. So to do that, we're just going to plot the data. So I'm going to highlight all of the X and Y values, go to Insert, and in the chart section, I'll choose the scatter plot type. And I'm going to make this a little bit smaller so it fits in my space here. And I'm going to delete the chart title, but I am going to add some axis titles. So it's not super important here because here the axis titles are just X and Y, but this is really important later when we have different types of data, so we know exactly what we're looking at when we go to make conclusions. The other thing we can do here is actually add a trend line and an equation for that trend line. To do that, we'll go to Add Chart Element, still with the chart selected, and we'll select Trend Line and Linear. And then you'll see that this little dotted line appears. If you click on that line and then double click on it to pull up the formatting section, we'll see the trend line options on the right. And if you scroll down, you can choose Display Equation on Chart and Display R-squared value on chart. So this is a really simple way to get some of the information you need for these types of problems without doing a whole lot of work. Unfortunately, it doesn't tell us anything about the correlation or the significance of this correlation or R-squared value. So we do have to do that a little bit differently. But this is a good way to start. And so far, even without that equation, we see that this data does look pretty linear. That line isn't too far off. And the data points generally follow a linear pattern. There can be points that are a little bit more offset. Those might be outliers, but as long as the general pattern is linear, you can go ahead and proceed with the correlation or regression analysis. So let's go ahead and in this section on the right, we'll do all of our correlation testing. First, we'll start with what are our correlation hypotheses. And for correlation, the null hypothesis is simply that R equals 0, that correlation coefficient is equal to 0. Our alternative is that R is not equal to 0. Here we go. Okay. Next, we'll use the data analysis toolpack to analyze this data. So to do that, click on the Data tab, and on the far right, you should have the Data Analysis button. And we'll click on Correlation. And the input range, we're going to select all of the X and Y data. And this is really important. Make sure you do pay attention to how to do the correlation versus the regression because they are different. The data is grouped by column, so we don't need to change that option here. I did highlight the labels, so I'll select this option here. And for the output range, I'm going to go ahead and put it in this spot here. It's a very small output, and we'll hit OK. And there we have it. So this is kind of a different table, and it doesn't really tell you what you're looking for unless you already know. What you are looking for is this value here, the intersection between X and Y. So I'll go ahead and highlight that here. This value is the correlation coefficient. So our correlation between X and Y is negative 0.878. So in this cell here, I'm just going to put equals and reference that cell. Next, to determine if this correlation is significant, we'll use a formula to calculate the t-calc value and then calculate the p-value from the t-calc value. So the formula is shown here on the template. It's equal to the correlation coefficient times the square root of the number of observations. So I'm going to do several formulas within this one formula. You can separate these out as needed if you'd like. So to find n, I'm going to use the count function, and I'm adding another parentheses here because this is going to be the numerator of what's inside the square root equation. So this will be count, and I'm just going to select the y values. This is the number of observations made. So this is count the number of observations minus 2. And that's my numerator inside the square root function. I'm going to divide that numerator by 1 minus the correlation coefficient squared. And for squared, I use the little hat symbol to close parentheses for the denominator, close parentheses for the square root, and press enter. And we get negative 4.859 and a bunch of digits after that. So that's great, but what do we do with that? We need to then calculate our p-value. This is using a formula we've seen quite a bit before. So this is t.dist.2t because this is a two-tailed test. And then we're going to take the absolute value of the t-calc. So we always want the positive version of the t-calc. There is a function in Excel to do that for us. it's ABS, and then I'll select my tcalc value. So that's the first argument. The second argument is the number of observations minus 2. So here I'll also use count, selecting just the y values, closing that parentheses, and subtracting 2. And we get a p-value of 0.0018. Since this p-value is less than 0.05, we reject our null hypothesis. So let's go ahead and type that into our conclusion sections here. So we'll reject the null because p is less than alpha. And our biological conclusion, and I have biological in quotes here because this is just x and y, not a biological data set. Our biological conclusion would be that there is a significant correlation, and that correlation is negative because of the negative 0.87. So significant negative correlation between x and y. So if this were actually a biological data set, you would want to describe those variables in that conclusion. The last section I have here for correlation in Excel is a question, and it's under this correlations prediction section, and it asks, if x equals 25, can you predict what y would be? And a lot of people, they'll just come up here and they'll look at the chart and they'll be like, sure, I can. I have the formula, I can plug it in and calculate what y is. But really important for correlation, we cannot make predictions. So do type this in with me, and do not forget, you cannot make predictions with correlation data. You can make it with regression data, and we'll cover that in the next part of the lecture. Okay, so that is all of correlation in Excel. So I'm going to go ahead and pull up the PowerPoint again so we can talk about our regression. So as I mentioned at the beginning of the lecture, one of the purposes of regression is to be able to predict values of y given values of x. Regression analysis estimates the equation for the best fitting line for the data. This line describes how the dependent variable, or that observed variable y, changes as the independent or manipulated variable x changes. The resulting equation from this analysis is y equals a plus bx, and hopefully this looks similar to the equation for a line, which you've seen before, y equals mx plus b. So here the important things to look at are a, which is the y-intercept value, and b, which is the slope. Then we have x and y, which x is that independent variable and y is that predicted value of y at x. The resulting calculated statistic for the regression analysis is the coefficient of determination, and this is notated with a capital R squared. R squared defines the proportion of variation of y that is explained by the variation in x. And that's kind of a weird conceptual topic. I'll have some slides showing what that looks like graphically to hopefully clear that up a little bit. For regression, there are 5 major assumptions for the data. The first is the relationship between x and y is linear. This is the same assumption as for correlation. The second is the independent variable x values are fixed. They are known exactly. So we know exactly how much of something we're either putting into or taking out of, or time lengths. These are not observational values. This element is controlled, it's manipulated by the researcher. So that is the main point to differentiate regression from correlation. The third assumption is that the variation of the dependent variable y is normally distributed around the regression line. Fourth, the variations of y at each value of x are homogeneous. And fifth, the observations are independent of each other. This would mean that there's no paired values within the data. The most important assumptions for the lab portion of this class are the first 2. So first, we must always check that the relationship between x and y is linear. And for regression in particular, we need to know that the independent variable values are fixed. This is not an observational value. The other 3 can be checked in R. We're not going to do that in this class though, because it's a little bit too advanced for this course. So here I am going to break down a little bit of the math for regression in order to be able to show you what this looks like on the graph. So again, this calculated statistic, R squared, the range for R squared is 0 to 1. So remember, for the lowercase r for correlation, the range was -1 to 1. Here, R squared is 0 to 1, and this value indicates how much that regression line explains how y varies according to x. To calculate R squared, we use the sum of squares for regression divided by the sum of squares for the total. I'm going to keep going through this, so bear with me. The sum of squares for the total is equal to the sum of squares for the regression plus the sum of squares plus the residual, and each of those is calculated with this summation notation of different portions of y subtracted from the predicted values of y or the mean values of y. You don't need to know exactly what these formulas do, or you don't know how to do them in Excel by yourself, because we have the tools to do them for us, but I am going to show you what this looks like in the next slide. So notice that the regression is in yellow. This is the explained variance. The residual or error is in purple, and this is the unexplained variance. So what the regression line does not account for. Okay, so here we have some data. The data points are in red. So these are our observed values. Each one is y subscript I. So these are observed values for those points at x. We have our mean value, which is y bar, in green. And then we have the regression line for this data in blue. On the regression line, we have many, many predicted values. So these are y subscript I with a little hat on top. These are the predicted values where y would be on this regression line for that point at x. Between the predicted value and the mean value is the explained variance. This is the regression. So this is how much of the variance is explained by the blue line for this point on the x-axis. The difference between the predicted value and the observed value is the unexplained variance. This is called the residual or error. And this variance is what the regression line cannot explain for that data point. I'll show you the same thing on the other side of this graph. So we have another predicted value, which is the y subscript I with the hat. This is on the regression line. The difference between that predicted value and the mean is the explained variance, which is the regression. And then the distance between the predicted value and the observed value is the unexplained variance, that residual or error term. All in all, we use this to find R squared, which is the regression, that explained variance, divided by the total variance, which is simply the regression plus the residual variance. Again, you don't need to know how to do all this math by hand because we have tools that will do it in Excel and R. But hopefully this kind of clears up what this means, the difference between regression and residual, and how to calculate R squared if you need to do it by hand for another class. Okay, so for significance of regression analysis, we have our hypotheses here. The null hypothesis is that B, or the slope of the regression line, is equal to 0. So like correlation, this would mean that there's no relationship between our two variables. Our alternative hypothesis is that the slope does not equal 0. The slope can be positive or negative, and this would indicate some positive or negative relationship between the two variables. Ultimately, an ANOVA or a t-test is used to test for the significance of these values, but R and Excel do it for you, so we will not be doing those by hand. To interpret the resulting p-value from our regression analysis, if p is less than alpha, as always, we reject our null hypothesis. This would indicate that the slope is significantly different from 0, which would allow us to conclude that there is a significant and non-random association. There's some relationship between these two variables, and as the independent variable, or x, increases, the dependent variable, y, can be predicted based on an equation. That is another major difference between regression and correlation. Regression does allow you to predict values of y given values of x. On the other hand, if p is greater than alpha, we accept our null hypothesis and conclude that there is no relationship between the two variables. The p-value of the regression analysis lets us know if this is a significant relationship. Here are some examples of what the slope can look like from this analysis. If the slope is equal to 0, like in this left graph, we know that there's no relationship between x and y. If b is less than 0, so slope is less than 0, this is a negative relationship. So as x increases, y decreases. Finally, if b is greater than 0, we have a positive slope. So as x increases, y increases. And these are good ways to help shape your conclusions because we are interested in how the two biological variables influence each other. So that is the end of this PowerPoint. We're going to go ahead and do the regression worked example in Excel first, then we'll do it in R, and then we'll do one more example in R. So let's go ahead and go back into the Excel template because we're going to use the same data as we did for the correlation analysis. So again, whether this was a correlation or a regression problem, the first step is to always plot the data. So we've done that here. We also know the trick to how to already get the equation and the R² value from this data. For regression, the hypotheses were already listed here. Let me delete those, we'll type them together. The null hypothesis for regression is that the slope, or b is what it says in the slides, is equal to 0. The alternative is that the slope b is not equal to 0. All right, so for the regression, we're still going to use data analysis toolpack. But this is going to be different than the correlation. So scrolling down and selecting the regression tool, be very careful with the input ranges because the first one is the input y range, and it just says y. Y represents the observed variable, the one that is not being manipulated by the researchers. This is an observational value only. Again, kind of difficult to see with this problem because it isn't a biological question. So we will look at that again with another question from this chapter. So the first one is the input y range. I'm going to go ahead and select everything, and I always like to select the label as well because this does affect how it appears in the final results tables, making it a little bit easier to interpret. Then for the input x range, I'll also highlight everything, including the label. And because I included the labels, I have to select labels here. We're going to leave the confidence interval at 95%. This is just leaving alpha at 0.05. And then for the output range, I am going to put it in this worksheet. I'm going to select this cell here, leaving a little bit of space. Press OK, and this is a huge output, very different from the correlation, which was a very small little table here. So I've left some notes on this table as well, so we can easily find what we need, because this is a lot of data and we don't need all of it. So the first thing we'll look for is our actual R² value. This value is located in the first table, and it is right here, R². So I'm going to go ahead and highlight that. So that's the first value we're looking for. The next set of values we're looking for are the values for the equation of the regression line. Those are located in the third table under this coefficients header. So we have the intercept value here, 49.63, and the slope value here next to x, negative 0.7459. So I'll go ahead and highlight those as well, and you can scroll up and check those are the same values we got up here. The last value we're going to get from this analysis is the p-value for the slope. That's located in the column for p-value, specifically the second one. So this x represents the slope, so we only are interested in the p-value for the slope, and that is 0.0018, so I'll highlight that here. And if you did the regression with me on this template, you'll see that these autofilled. This did not autofill all the way because it doesn't like this function anymore. And you don't need to know how to do this part, this concatenating function. I just think it's fun to have there. You can double click in there and look at how this function works if you're interested. So now we have our regression line equation, our slope p-value, and our r-squared value. That's everything we need for the regression analysis. Based on the p-value, which is less than 0.05, our statistical conclusion is to reject our null hypothesis because p is less than alpha. Again, biological in quotes here because it's not really biological, but just an example. Here our conclusion would be that the relationship between x and y is significantly different from 0. We can also conclude the direction of this. So let's take a look at the graph again. So as we see x increase, we see y decrease. So let's go ahead and note that here as well. As x increases, y decreases. Again, that would be a little bit more interesting if we had some actual biological values to work with, but for here, those will kind of just be placeholders for you to use later. The last thing in Excel for our regression analysis is predictions. So remember, with correlation, we absolutely cannot make predictions. That equation means nothing for correlation analysis. For regression, that equation can be used to predict y values. So this asks the same thing as the correlation one up here. If x is equal to 25, can you predict what y would be? I'll put an explanation here. The answer is yes, you can make predictions from regression analysis. All you have to do is plug in the variable to the equation and solve. So here, let's go ahead and solve this one if x equals 25. So here's our equation, and we have all our values already highlighted for us, so we don't have to type in too much. So equals the 49.631, that y-intercept, plus the x, the slope value, multiplied by 25. And we get a y value of 30.984 if we round. And if we go back up here and look at our graph, we can see that at about 25, we look up on the regression line, that looks to be right above 30, and we got around 31, so we know that's probably an accurate estimate and that we did our calculations right. So make sure you know how to do this as well, these predictions from regression analyses. The next thing we're going to do is all of this in R. So I'm going to go ahead and take this original data. I'm going to copy it, copy this onto a new workbook, and paste that in. I'm going to save this file as a CSV, and I'm going to go ahead and work on my desktop again. And this one I'm going to call Chapter 19. And we need to change the format to a regular CSV file. And let's go ahead and go into R with this data. Remember, when you first open RStudio, you'll only have 3 panels, the console, the environment, and the plots. We need to make a new R script so we can save all of our functions and data up here. And the R script is all you need to turn in for assignments and exams because I can run your R script on my own computer. So the first thing we're going to do, I'm going to title this section Regression, is load in the data. So I'm just going to call this data equals read CSV, And I tend to forget to set my working directory before I get started, and then I start typing and realize I need to set my directory. So we're going to choose our working directory. I saved my file to the desktop, and my file was called chapter19.csv. It does have column names, so we set the header to true. When we run that line, we see ran successfully. We now have imported this data to R. Let's go ahead and take a look at it with head of data. And we see our X and Y values. Remember that head only shows the first 6 rows of the data. You can run the line with just the object name data to see all of the lines, but you don't have to. Head of the object name is sufficient. So the next thing we're going to do, just as we would in Excel, is plot this data to make sure it's linear and that we can run a regression analysis. To do this, we use the function plot, and we're going to do data Y according to data X. So we always want to do the Y, or the observed, the dependent variable first, according to, with this little squiggle, the X, or independent, that manipulated controlled variable. When we run this, we see a nice plot here. This one looks a little bit different than Excel because the X-axis is from 20 to 35 now, and the Y-axis is also shifted so that the data fills more of the screen. So again, this looks pretty linear. They're a little dispersed, but not too much. So this would meet the assumption for linearity, and we can proceed with the regression analysis. The regression analysis is kind of similar to the ANOVA, where we need to store the results and use the summary function. So I'm going to go ahead and call this next object data R for regression. And this is the new function for the regression analysis. This regression analysis is done with the function LM. And just like with the input to plot, we do the data Y value according to the data X value. And when we run this, we don't see an output yet because we just assigned the regression analysis to the object called data R. So now we can do summary of data R, just like we did with the one-way ANOVA and the two-way ANOVA. I'm going to make this a little bit bigger here to point out the things you need to look at, because this also looks pretty big, just like it did in Excel, but there's a few things we need to focus on. So the first thing, if we go in the same order as Excel, is the R² value, and that's down here at the very bottom of the output. It's called the multiple R², and we get 0.7713, which matches the one we got in Excel. So that's the first one. The next are the A and B values for the equation of the line. Those are found in the coefficients section here under estimate. So we have the estimate for the intercept, that is A, and the estimate for the slope, or B. And you'll see that these numbers match the Excel values as well. The final value is the P value for the slope. And just like in Excel, it's in the row for the slope. And here it can be found under this PR greater than T value here. So 0.00184. So we get the same values and same conclusions as we did in Excel. Let's go ahead and type some of those in here. And actually what I'm going to do is I'm going to go ahead and type my hypotheses up here too for regression. The null hypothesis was slope equals 0. And the alternative was slope does not equal 0. And from my summary of the regression analysis, let's go ahead and type in the R² value. You can also just type in R2 is 0.7713. The equation for the regression line is Y equals, and I'm just going to do it in the MX plus B format because I'm a little bit more used to using that. I'm sure you guys are too. So the slope is this value here. You can copy and paste that. So negative 0.7459x, or I'll do a lowercase x, plus 49.6311. I'm going to space this out just a little bit. And finally, the p-value for the slope is, and that is again under this PR column for the slope, so 0.00184. So our conclusions using R will be the same as using Excel. So I'm going to go ahead and type in statistical conclusion, which is to reject the null hypothesis because the p-value is less than alpha. And our biological conclusion is X and Y are significantly and negatively, again, that negative slope value, negatively related. And this is another way of writing what we wrote in Excel, but I'll include here as well as X increases, Y decreases. Okay, so I'm gonna make this a little bit smaller so we can see this whole thing. The last thing we're gonna do that's new in R is add the regression line to the plot. To do this, we'll use another new function, and this is called AB line. And the argument for AB line is the results from the regression. So we called our results data R. And when we run this line, we really quickly get a nice regression line through our data. So that concludes all of the regression for this worked example. Let's go ahead and do correlation as well for this worked example in R because it is super easy. The function for correlation in R is core.test. And here we'll use data Y and use a comma, data X. It's still in the order of the dependent variable first and then the independent variable, but here we'll use a comma. When we run this line, we get another kind of long output, but not quite as bad as the first one. All we need to focus on here first is the correlation value, negative 0.878, which is what we got in Excel, and our p-value here, 0.001837. That was a really quick way to do our correlation test in R. So let's go ahead and write some of those conclusions here. And actually, I'll do what I did to be consistent with the regression. I'll write out those hypotheses here as well. So the null hypothesis for correlation is R equals 0. The alternative is R does not equal 0. So here we have the correlation coefficient, and you do not have to type that out. You can just say R is this negative value. I'm going to copy and paste that. And then since P is 0.001 is less than alpha, reject the null. And then our biological conclusion would be there is a significant relationship between X and Y. You can also write the relationship is negative because it is a negative correlation value. So the last thing we're going to do here is take a look at two practice problems in the lab manual to understand how to determine whether this is a regression or correlation problem. Because the rest of the problems, you're only going to do one of these tests, not both, because you really can only choose one or the other for these data. So let's go ahead and go back into the lab manual. And I'm going to scroll down to page 258. And we'll be looking at questions 1 and 2. So in question 1, it says a corn farmer wants to determine the relationship between the amount of a phosphorus fertilizer and the percent sugar in some corn. So what he did is he applied different amounts of fertilizer, so 10, 20, 80, 60, etc., kilograms of fertilizer to that plot. And then he measured the amount of sugar in the corn after a couple of weeks. In this example, the farmer is controlling the amount of fertilizer, but he's not controlling the amount of sugar because that's just what's produced by the corn. So in this example, we have a controlled variable and an observed variable, or a independent and dependent variable. So this would be a regression analysis. Scrolling down to question 2, we have the Pacific Electric Ray, which is found off the coast, and to the right are the lengths and weights of some of these rays that were inadvertently trapped at a local power plant. So they're interested in the relationship between the length and weight of these rays. Neither of these variables can be controlled directly by the scientists, so both of these are observational variables. We don't know which one is controlled. Any of those conditions met, this would be a correlation analysis. We cannot determine which variable is affecting the other, so this is correlation instead of regression. So that's always how you can go through this thought process for the rest of these practice problems. What we're going to do now is question 1 just in R, and we'll do that pretty quickly because we've already gone through the steps. So I'm going to go ahead and I'm going to open the Excel template again because I have this data already typed in here. So the amount of phosphorus fertilizer and then the resulting amount of sugar in the corn. So I'm going to go ahead and copy this data into a new CSV, but before I do that, I do want to clarify something that I don't think I've explained very well about combining data onto a single CSV file for work in RStudio. So while you can certainly paste this data in the same Chapter 19 CSV we used earlier, what this would do is it would prevent you from going back to doing any work with the X and Y columns again. The reason for this is the phosphorus and sugar data has an extra row of data than the X and Y columns do, and R would kind of interpret these blank rows for X and Y as NA values. This will throw off some of the analysis for the data. It won't necessarily change it for a regression, but it will definitely change it for things like ANOVAs. So I do apologize that I wasn't more clear about that earlier. The safest method for working with this data in R is to just make new CSVs for every problem. So I'm going to go ahead and undo the pasting of this new data into this Chapter 19 CSV. I'm going to leave this one as is. Instead, I'm going to go ahead and take this phosphorus and sugar columns and make a new blank workbook with this data. This one I'll save also to my desktop, and I'll save it as Chapter 19, Question 1, and as a CSV. Okay, so now that I have that, I'm going to go back into RStudio and I'm going to space down a few rows and make a new kind of header to separate question 1 from the worked example above. And as we discussed, question 1 will be a regression analysis as long as it meets the assumption of linearity. So let's first load in the data, and we'll just call this Q1. read.csv, and again, you can use any type of descriptive object name for this problem. I'm using Q1, but you could use things like corn or fertilizer, something like that, to just let you know which problem you're working on. And I'm going to import my Chapter 19 Q1 CSV, which does have column names, so I'll set the header to true. Once I do that, I'll take a look at the data using head Q1, make sure everything imported as I expected to, which it looks like it did. And then I'm going to go ahead and plot the data using plot Q1, again with this Y value. So the Y value here is the sugar, the percent sugar in the corn. It is the dependent variable, what's being tested and observed. And we're going to plot the sugar according to the Q1 phosphorus. So that phosphorus is the independent variable. It's what the farmer specifically controlled those numbers for. And when we plot that, we see on the plot section that we do have a pretty nice linear display of this data. And one thing I didn't mention earlier is that when we're looking at this data, we're not necessarily looking for linear or not linear. We're looking for linear or other types of data patterns like exponential, log, sine, things like that. If the data doesn't look linear as is, we do have to transform that, and that is actually the last thing I do before we completely end this video. But right now, this looks like it mostly follows a linear pattern. It doesn't look like an exponential curve like this, or a square root curve or something like that. So because of this, we can do a regression. So since data is linear, we can do regression. And let's go ahead and type out our null hypothesis, which is that the slope is equal to 0, and the alternative is the slope is not equal to 0. So the next thing we'll do is the actual regression analysis. So I'll save that to an object called Q1R for regression, and LM. Again, that LM stands for linear model. Unfortunately, it's not quite as simple to remember as the correlation test, but we do have to know it's LM for regression. The good news is it is the same arguments as the plot. So it is the Y value, that dependent variable of sugar, according to the independent variable X, phosphorus. And then we'll do summary of Q1R to look at our results here. And I'm going to go ahead and pull out these values and type them into my script so I don't have to run that again. So the first thing I'll take a look at is the R squared value. And that's down here, the multiple R squared, so 0.9461. And I'll copy and paste that. The next thing I'll get is the equation of the regression line. So that will be Y equals, and I'll start with the slope, so 0.192 times X plus 5.13. And the last thing I'll type here is the p-value for the slope, which is located in this row for the slope and in the column for PR, and that's very small, much less than 0.05, which would indicate to us that we should reject the null hypothesis for the regression analysis. Before I go into those conclusions, I am going to add the regression line to the plot using the AB line function with the Q1R regression results, and that gives us a nice regression line here. And we have our phosphorus values on the x-axis and our sugar values on the y-axis. So over here, let's do our statistical conclusions, or really only one conclusion, and that is to reject the null hypothesis because p is less than alpha. And here, our biological conclusion. Now we want to really talk about these two variables in the problem. And remember, this problem is talking about a farmer who's testing the relationship between the amount of phosphorus fertilizer and the resulting percent sugar in ears of corn. So here we found that they are significantly related in a positive way. So the amount of phosphorus fertilizer and the percent sugar in the corn are significantly related. As the amount of fertilizer increases, so that's on the x-axis here, the percent sugar also increases, and that's shown on the y-axis here. That's also shown with our positive slope value. I'll make one more note here. We can predict X, or the percent sugar. We can predict Y, which is the percent sugar, if given X, which is the phosphorus fertilizer. So again, we can only make those predictions with the equation of the regression line for regression analyses. We cannot do that for correlation analyses. Okay, so the very last thing we're going to do here is take a look at what we need to do when the data isn't linear. And just a disclaimer for this class in particular, you won't see this happen too often, but it does happen with regular data that we just go out into the field and collect. So I'm going to space down a little bit again and make a new section for question 2. And this is the electric ray question where we have the lengths and weights of different rays collected at a power plant. And this analysis would be a correlation analysis because we are not controlling either one of these two variables. So this data is not in the Excel template. I will post it though later. So right now I actually have it in my downloads folder, so I'm going to cut and paste that into my desktop. And I'm going to rename this as chapter 19 Q2. And again, I will have this on the template that I post for you. So just taking a look at this, this is just the same data from the lab manual. So we have the different lengths and weights of these electric rays. So I'm going to do this portion in R, but you can do the exact same thing in Excel and get the same results. So the first thing I'm going to do is load in the data. So Q2 is read CSV, chapter 19, Q2, and there is a header. And I'll do head Q2 just to make sure it imported correctly. And then I'm going to plot Q2. And for this one, since we're not doing a regression, so there isn't an independent and independent variable, you can do length or weight on the y-axis. It's up to you. I'm just going to go in order and do length first and do according to the Q2 weight. And when I run that, I see that it starts to look a little bit linear, but it does start to kind of plateau off like this. And this is actually looking like a non-linear pattern. Because of this, we need to transform the data in order to do a correlation analysis. And this is just as we've seen with other types of statistical tests. So the way I'm going to do this is I'm going to do Q2 $, and I'm going to call a new transformation log of the weight, and I'm going to do the log of, or the log 10 of Q2 weight, and that will give me a new column of data with the log 10 values of the weight. Now I'm going to copy and paste the plot function, and instead of doing length versus weight, I'm going to do length versus log weight. And now we see a much more linear pattern. So if you use the arrows here at the top left of the plots button, we see how we went from a plateaued kind of graph into a much more linear graph. So we still have a couple dots that are a little bit outside of the line here, but it's an improvement to the plateau shape we saw here. So this log weight data is what we would want to use in the correlation analysis, which I'll do here. So for the correlation, we need to do core.test. And the inputs here are y, then x. So here we have the length as y, so we'll do Q2 length, and then Q2, again using the log value in the actual test. And here we get our correlation value of 0.917. Our p-value is less than 2.2 times 10 to the negative 16th. If you get this kind of value, this is what you can answer on your answer sheet. You don't have to go and calculate the actual p-value here. But what this tells us is there is a significant positive correlation between the weight and length of these electric rays. So the last thing we'll do, as always, is save this R script. So I'll go ahead and save the R script, still on my desktop, chapter 19, regression and correlation. Save, and I did have one there, so I'm going to replace it. And I just want to show you one more thing on this desktop. So now I have 1 to 3 CSVs that I've used in my one R script. If I were to turn this in for an assignment or exam, I would turn in all 4 of these files, plus any Excel files that you did other problems in or had an answer sheet or something like that. They would all be turned in so that I can run your script from start to finish with the data that you used. And with that said, that will conclude this video on Chapter 19.